Welcome to DAR Tutors for online and home tuition. Today we're covering a fundamental topic in statistics, sampling and data. By the end of this video, you will be able to, first, identify and explain common errors in data collection. Second, describe and apply various sampling methods, including random, systematic, stratified, quota, and convenience sampling. Third, classify data as categorical, discrete, or continuous. Fourth, create and analyze frequency tables, column graphs, and histograms. And fifth, write clear and unbiased questions for surveys. We'll be working through examples from the IB Mathematics, Applications and Interpretation HL curriculum to ensure you're well prepared. Let's begin by defining some key terms. In statistics, our goal is to collect information, analyze it, and then use that analysis to draw conclusions about a larger group. This larger group is called the population. It's the entire collection of individuals we are interested in. Often, the population is too large to study completely. Think about trying to survey every single student in a large city. It's simply not feasible. In such cases, we collect data from a smaller, manageable subset of the population called a sample. A study that involves every member of a population is called a census. A perfect example of a census is a national population count. But in most statistical investigations, we work with samples. When we analyze data, we look at variables. A variable is a characteristic or attribute that we can measure. Variables can be categorized into two main types. First, we have categorical variables, also known as qualitative variables. These describe a characteristic that can be divided into distinct categories. For example, a person's hair color, favorite type of music, or the country they live in are all categorical variables. Second, we have quantitative variables. These are numerical values that can be counted or measured. For instance, a person's height, their age, or the number of items they purchased are all quantitative variables. Remember, the distinction between these two types is crucial because it often determines the best way to analyze and present your data. Now that we understand what a population and sample are, let's explore the process of a statistical investigation. This process typically follows 6 steps. The first step is to state the problem. You must clearly define what you are investigating. This involves identifying the population of interest and the variables you intend to measure. Without a well-defined question, your investigation will lack focus. For example, asking how big is an elephant is too vague. We need to specify what big means. Are we measuring height, mass, the circumference of its trunk? Clearly defining your terms is essential. The second step is to choose a sample. As we've discussed, it's usually impossible to study an entire population. So, we must select a representative sample. The key here is representative. The sample should accurately reflect the characteristics of the population to avoid bias, which we will define more rigorously soon. Next is to collect the data. Once the sample and variables are chosen, you need a method to gather the data. This might be through surveys, experiments, or observations. The method must be appropriate for your investigation to ensure the data collected is valid. Step 4 is to organize and display the data. Raw data can be difficult to read. Organizing it into tables and displaying it with appropriate graphs makes patterns and features much clearer. We will learn how to do this later in this video. The 5th step is to calculate descriptive statistics. These are numerical values that summarize the data, such as measures of central tendency like the mean and median, or measures of spread like the standard deviation. They give us a more precise understanding of the data's characteristics. Finally, the 6th step is to interpret the statistics. This is where you draw conclusions and connect your findings back to your original problem. You must describe what the data and your calculations tell you about the population and determine if your initial problem has been answered. This systematic approach ensures that statistical investigations are logical, thorough, and scientifically sound. Mastering this process is key to your success in IB Mathematics. Even when a statistical investigation is conducted carefully, it's virtually impossible to avoid all mistakes. In this scene, we will cover the main types of errors. The first type of error is sampling error. This occurs simply because we are using a sample instead of the entire population. It's the natural difference that exists between a sample and the population from which it's drawn. This error is random and can happen even with a perfectly chosen, unbiased sample. For example, If you measure the average height of 100 students in a school of 1,000, your result will likely be slightly different from the true average height of all 1,000 students. This difference is sampling error. The second type is coverage error. This happens when the sample does not accurately reflect the population. In other words, certain subgroups of the population are underrepresented or overrepresented in the sample. A sample with coverage error is called a biased sample. Let's consider an example. Suppose a school counselor wants to know students' opinions on the school yearbook design. If she only surveys her own homeroom class, this would be a convenience sample. Is it likely to have coverage error? Yes, it would be biased. Why? Because her class might not be representative of the entire school's student body in terms of age, interests, or involvement in extracurriculars. To avoid coverage error, the sample needs to be large enough and selected in an unbiased way. The third type of error is non-response error. This happens when a significant portion of the selected sample fails to respond to the survey. This is common in online surveys, where many people simply ignore them. Non-response error is a form of coverage error because the non-responders might be different from the responders in a significant way. For instance, in a customer satisfaction survey, people who are very unhappy are often more motivated to respond than those who are content. The resulting data would therefore overrepresent dissatisfaction. Finally, we have measurement error. This refers to inaccuracies that occur during the actual data collection process. This can be caused by faulty measuring devices, unclear or biased survey questions, or even human error in recording data. Imagine a student measuring the height of 100 seedlings with a ruler that is not properly calibrated. Or a survey question asking, "Do you support the dangerous practice of cycling without a helmet?" The word dangerous biases the question and influences the answer, leading to measurement error. A better question would be neutral, such as, should cyclists be required to wear helmets? Understanding these errors is essential for evaluating statistical investigations. Let's work through some IB-style examples from Exercise 12A. Here is our first problem. Take a moment to consider the question. What makes a conclusion reliable? The sample. Is a sample of only 7 patients representative of the entire population of high blood pressure patients? Probably not. So the answer is no. This sample cannot be used to draw reliable conclusions. The sample size is too small, creating a large sampling error, and it's unclear how the patients were selected, so there could be coverage error. A much larger, randomly selected sample would be needed to make sound inferences. Let's move to a second example. Here is our second problem. Again, let's think critically. The conclusion is about all people in Canada, but the survey was only conducted in a shopping mall in Toronto. First, there's coverage error. A sample from a Toronto shopping mall is not representative of the entire country of Canada. People in other provinces or rural areas might have different opinions and experiences. Second, there's a strong chance of measurement error from bias. People in a Toronto shopping mall, a major hockey city, are probably more likely to have been to a hockey game than the average Canadian, which would skew the results. Now that we understand the importance of avoiding bias, we'll look at the best way to do so. Choosing a sample randomly. This ensures that every member of the population has an equal chance of being selected. The first method we'll cover is simple random sampling. In this method, a sample of size n is selected from a population in such a way that every member of the population has the same chance of being chosen, and every possible sample of that size n has the same chance of being chosen as any other. It's like putting all the names in a hat and drawing them out. A more practical method for larger populations is to assign a unique number to each member and use a random number generator. For example, if we have a class of 30 students and want a simple random sample of 3, we can number the students from 1 to 30. Then using a calculator's random integer function like rand_int133, we might get the numbers 8, 12, and 25. Students 8, 12, and 25 would then form our sample. The key advantage of simple random sampling is that it is free of bias. The main disadvantage is that it can be time-consuming to implement for very large populations, as it requires a complete list of all members. Let's look at another random sampling technique, systematic sampling. Systematic sampling involves selecting members of a population at regular, fixed intervals. This method is often more practical than simple random sampling when dealing with large ordered populations. The process is as follows. You divide the population size n by the desired sample size n. This gives you an interval k. Then you choose a random starting point from the first k members and select every kth member from there. For example, a large city store wants to sample 5% of its customers to gauge interest in a new product. 5% equals 5 × 100 balls equals 120, so k equals 20. A starting customer is selected at random from the first 20. Let's say, using a random number generator like rand_int y20 the store chooses customer number 7. Then they would survey the 7th, 27th, 47th, 7th customer, and so on throughout the day. This method is useful because it's simpler to implement in a real-world setting. However, it can be problematic if there's a cyclical pattern in the population that aligns with your sampling interval. For example, if you survey every 7th day, you might always survey on the same day of the week, introducing bias. So far, we've focused on random methods. Now, let's look at a non-random and often problematic method: convenience sampling. Convenience sampling is, as the name suggests, a method where individuals are chosen simply because they are easily accessible or willing to participate. It's the least scientifically rigorous of the methods we will discuss. Let's revisit our earlier example. Suppose a researcher wants to survey public opinion on environmental issues. They stand in a pedestrian mall and interview people as they walk past. This is a classic example of a convenience sample. The researcher might approach people who are walking slowly, are not in a conversation, or simply look friendly. These are not random criteria. They are based on convenience. This immediately introduces bias. The sample of people in the mall is unlikely to be representative of the wider population. It might include more young people, more people who live nearby, or more people who have time to stop and talk. This creates a coverage error, as certain demographics are either overrepresented or underrepresented. Therefore, the answer to the question, do convenience samples often produce a biased sample, is a resounding yes. Because convenience samples are not random, they almost always lead to coverage error and thus biased results. They should be avoided unless no other method is possible, and the researcher is prepared to acknowledge and account for the significant bias. Two other important sampling methods, stratified sampling and quota sampling, are useful when your population can be naturally divided into subgroups or strata. Stratified sampling involves splitting the population into distinct, non-overlapping groups called strata. Then you perform simple random sampling within each stratum. The sample size from each stratum is proportional to the stratum size in the population. This method guarantees that all key subgroups are correctly represented in your sample. Let's work through an example. Imagine a school with 752 students across 5-year levels, and you need a sample of 50 students. To get a stratified sample, we must determine how many students to select from each year level to make it proportional. For year 8, we calculate its proportion of the total student body and multiply it by our target sample size of 50. That's 137 divided by 752 times 50, which is approximately 9.1. We can't sample 0.1 of a student, so we round to 9. We repeat this for every year level. We'd then need to use a random sampling method, like a random number generator, to select exactly 9 students from the year 8 list, 10 from year 9, and so on. This ensures our sample of 50 is a perfect microcosm of the school population, representing each year level accurately. Complementing stratified sampling is quota sampling. While they both involve strata, the key difference lies in how the final individuals are selected. Quota sampling also divides the population into strata, and it sets quotas or targets for the number of individuals to be included from each stratum. However, once the quotas are set, the selection of individuals is done non-randomly, often using convenience sampling. The surveyor will keep collecting data from each stratum until their quota for that stratum is met. Let's apply this to our school example. The quotas would be the same, 9 year 8s, 10 year 9s, etc. But with quota sampling, A surveyor might go to the school gates before school starts and ask every Year 8 student they see if they'd like to participate, until they have their quota of 9. Then they do the same for Year 9s, and so on. This is clearly a form of convenience sampling. This difference in selection is critical. Stratified sampling is a form of probability sampling because every individual has a known chance of being selected, while quota sampling is a non-probability method because the interviewer's discretion introduces bias. While it can be faster and cheaper than stratified sampling, the risk of bias is much higher. Here's an IB-style question to test your understanding. A counselor wants to survey students and needs to ensure both genders are represented. Should they use stratified or quota sampling? The best choice is stratified sampling. By stratifying by gender, the counselor could randomly select a proportional number of male and female students, giving every student a fair chance to be in the sample and minimizing bias. Quota sampling would likely introduce bias, as the counselor might inadvertently select more friendly or visible students of one gender over the other. We've now reached the 10-minute mark. Before we continue, I want to invite you to connect with us. If you're finding these explanations helpful and would like more personalized support, please contact DAR Tutors. We offer expert online and home tuition for the IB diploma, as well as A-level and IGCSE curricula. Our tailored lessons can help you master complex topics, prepare for exams, and achieve your academic goals. You can find our contact details on our website, dartutors.com. Sampling is the process of getting data, but once you have it, you need to know how to handle it. This requires understanding the different types of data. First, let's revisit categorical variables. Remember, these describe a quality, not a number. The data collected from them is called categorical data. A key feature is that you can't perform arithmetic operations, like finding the average, on categorical data. For example, if you collect data on the brands of toothpaste used by students, you'll get answers like Colgate, Oral-B, Sensodyne. The average toothpaste brand doesn't make sense. Next, we have quantitative or numerical variables, which give us numerical data. This data is further divided into two types, discrete and continuous. Discrete data takes exact whole number values. It's usually the result of counting. Think of the number of heads when flipping a coin 3 times. The answer must be 0, 1, 2, or 3. You can't have 2.5 heads. Other examples include the number of goals scored in a game, the number of siblings a person has, or the number of items in a shopping cart. Continuous data can take any numerical value within a given range. It's typically the result of measuring, and the precision is limited only by the measuring tool. For instance, the time it takes to run 100 meters. A runner might finish in 9.87 seconds, or 9.8765 seconds. The value is not restricted to whole numbers. Other examples are height, weight, temperature, and length. Understanding this distinction is vital. It will determine the type of graph you should use, the statistics you can calculate, and the conclusions you can draw. Let's practice with some examples. Let's apply our knowledge of data types to some IB problems. We need to classify each of these variables. Let's start with the number of brothers a person has. Can you have 2.5 brothers? No, you count your brothers. The value will be an exact whole number like 0, 1, 2, and so on. Therefore, this is discrete data. Next, the time children spend brushing their teeth each day. Time is something we measure. It can be 1 minute, 1.5 minutes, 2.05 minutes, etc. It can take any value within a range. This makes it continuous data. How about the brand of car a person drives? Brands are categories like Ford, Toyota, Mercedes. They describe a quality or characteristic. You cannot perform calculations on them. So this is categorical data. Finally, the diameter of bacteria colonies in CME. Diameter is a length, and length is something we measure. It could be 0.4 cm or any value in between. The precision is limited by our measuring device. This is a classic example of continuous data. Now that we can classify data, the next step is to organize it and display it visually. We'll start with simple discrete data. Let's say we collected data on the number of previews shown before a feature film for 30 cinema visits. The raw data is messy and hard to interpret. To make sense of it, we use a frequency table. The first column is the value of our variable, the number of previews. The second is the frequency, which is how many times each value appears. A tally column can be used to help with counting. Let's build the table. First, we identify the range of values, which goes from 1 to 6. Next, we go through the data, adding a tally mark for each occurrence. We use a diagonal line to represent the fifth tally. After counting the tallies, we fill in the frequency column. We can double-check our work by adding up the frequencies. 2 plus 7 plus 12 plus 8 plus 6 plus 3 equals 30, which matches our total number of cinema visits. The value with the highest frequency, 12, is called the mode. In this case, 3 previews were shown most often. We can also calculate the relative frequency, which is the frequency of a value divided by the total number of data points. This gives us the proportion or percentage of the data that falls into each category. A frequency table helps us organize the data. To get a quick visual understanding of its shape, we use a column graph. A column graph, also known as a bar chart, is used to display discrete data. Key features are: the x-axis shows the discrete values like 1, 2, 3, and so on. The y-axis shows the frequency. Critically, there must be gaps between the columns to show the data is discrete. Let's construct a column graph for our cinema preview data. The x-axis will show the number of previews from 1 to 6. The y-axis will show the frequency from 0 to our maximum of 12. For value 1, the frequency is 2, so we draw a column up to a height of 2. For value 2, the frequency is 7, so the column goes up to 7. We continue this for all values, making sure to leave a gap between each column. From this graph, the shape of the data or its distribution is much clearer. We can see that 3 previews was the most common. This shape can be described in a few ways. If both sides of the graph look like mirror images, it's symmetric. If the graph has a long tail pointing to the right, it's positively skewed. And if the tail points to the left, it's negatively skewed. In our example, the data is not perfectly symmetric. It has a slight tail stretching to the right, towards the higher values. We would describe this as being positively skewed. Sometimes, with discrete data, especially if there are many different values, a column graph can become cluttered and difficult to read. This is where grouping the data into class intervals can be very useful. We can group discrete data into class intervals to simplify its presentation. For example, if we were to count cars passing a kindergarten each day, we might get counts from 8 to 52. Plotting 40 different column heights would be unhelpful. Instead, we can create class intervals, such as 0 to 9, 10, 19, 20, 29, and so on. We then count how many data points fall into each interval. For example, suppose we have this grouped data. We can still draw a column graph for it, just as we did for ungrouped discrete data. The x-axis shows our class intervals, and the y-axis shows the frequency of each interval. Again, notice the gaps between the columns to indicate the data is discrete. From this graph, we can easily identify the modal class, the class with the highest frequency, which is 20 to 29 cars. Grouping the data gives us a clearer picture of the overall shape of the distribution. However, it also means we lose some detail. We know that one day had between 0 and 9 cars, but we don't know if it was 8 cars or 1 car. We've looked at displaying discrete data. Now let's turn our attention to continuous data. A special type of graph is used for this, the frequency histogram, or just histogram. When we measure data that is continuous, like height or time, it's very unlikely any 2 measurements will be exactly the same, even if we round them. So we can't use individual values on our x-axis. Instead, we must group continuous data into class intervals, just as we did with grouped discrete data. The histogram is very similar to the column graph, with one critical difference. The columns are joined together with no gaps. This is to graphically represent that the data is continuous. A column graph with gaps indicates discrete data, while a histogram without gaps indicates continuous data. Let's work through an example. Suppose we have the heights of a volleyball squad. Since height is a continuous variable, we are given a frequency table with class intervals. The interval 170 is less than or equal to h is less than 175 bars, means heights that are 170 centimeters or more, but less than 175 centimeters. To draw the histogram, we mark the class boundaries on the x-axis, 170, 170, 180, and so on. The frequency, 1, for the first interval becomes the height of the bar. We then draw the next bar immediately adjacent to it with a height of 8. After drawing all the bars, we have our histogram. The modal class, the tallest bar, is 185 to 190 centimeters. This tells us that more players are in this height range than any other. Describing the distribution is also straightforward. Looking at the histogram, we can see it's roughly bell-shaped, but with a slight tail to the left, so we could describe it as approximately symmetric or slightly negatively skewed. A key takeaway is that the shape of a histogram can tell us a lot about the data's distribution. Writing a good survey is more of an art than a science, but there are some fundamental guidelines to follow to ensure you collect meaningful data. Poorly worded questions can lead to misinterpretation and inaccurate answers. This is a common cause of measurement error. Let's review the key principles. First, keep questions simple and clear. Avoid jargon, ambiguity, and especially double negatives. A question like, "Do you disagree with not vaccinating children?" is confusing and difficult to answer. Second, be specific. General questions like, "Are you healthy?" can be interpreted in many ways. Is it physical health, mental health, social well-being? A series of specific questions like, "Do you exercise regularly? Do you smoke? Have you seen a doctor in the last year?" provides much better data. Third, choose your question type carefully. Unstructured questions allow for open-ended, free-form answers, which are great for exploring opinions. Structured questions provide a limited set of choices, which is good for collecting easily quantifiable data. If using structured questions, always consider adding an other option. Fourth, keep the tone neutral. Avoid emotive or judgmental language that leads the respondent to a particular answer. A question like, "Do you support the dangerous practice of cycling without a helmet?" is biased. A neutral alternative is, "Do you believe cyclists should be required to wear helmets?" Finally, be aware of personal questions. Questions about sensitive topics can make respondents uncomfortable, leading to untruthful answers or non-response. If you must ask a personal question, clearly justify why the information is needed. By adhering to these guidelines, you can write surveys that collect more reliable and valid data. Let's put these survey guidelines into practice with a final IB-style example. Consider the question, "Do you support the government's proposed cuts to education?" A journalist asks this question to 100 people. First, why might this produce a measurement error? The term cuts is highly emotive and carries a negative connotation. It frames the proposal in a negative light and is likely to bias the respondent's answer. People are inherently hesitant to support cuts to important sectors like education. The language itself is causing an inaccuracy in the measurement of the public's true opinion. It's not a neutral question. Now, how can we reword it to be more neutral and accurate? We need to remove the biased language. A much better question would be, "The government has proposed moving funding from education to health. Do you support this proposal?" This version is neutral. It simply states the facts of the proposal without judgment. It doesn't use the loaded word cuts. This allows respondents to give an answer based on the actual proposal, not just the word choice, thus reducing measurement error. We've covered the core concepts of sampling, data collection, and data presentation. To consolidate your understanding and prepare for the IB exam, let's work through 5 final comprehensive IB-style practice questions. Here is our first practice question. A local gym manager wants to understand the exercise habits of their 1,200 members. Part A asks us to classify the variable. The variable exercise habits is a characteristic or quality of the members, not a number. Therefore, it is a categorical variable. For Part B, we need a stratified sample of 150 members. This means we must select a proportional number from each age group. The total number of members is 1,200. First, we find the proportion of each group. The gym manager should randomly select 50 members from the under 25 group, 75 from the 25-45 group, and 25 from the over 45 group. Part C asks about a convenience sample. If the manager samples the first 150 members on a Monday morning, this will be biased. The early morning gym goers are likely to be more dedicated and have specific work schedules, which may not be representative of all gym members. Let's move on to practice question number 2. A factory produces light bulbs. A quality control officer records the lifespan of a sample of 20 bulbs in hours, as shown. Part A asks whether the data is discrete or continuous. Lifespan is a measure of time, which can take any value within a range. So, this is continuous data. For Part B, we need a frequency table with intervals of 50 hours. The lowest value is 870, so we can start our intervals at 850. We sort the data and count how many bulbs fall into each interval. For example, the first interval, 850 to 900, includes 870, 890, and 900, so its frequency is 3. Part C asks for the appropriate graph. Since the data is continuous, we must draw a histogram with no gaps between the columns. The x-axis shows the class intervals, and the y-axis shows the frequency. Finally, Part D asks us to describe the distribution. The histogram shows the highest bar in the middle and tails off on both sides. This is a classic bell shape, which is a symmetric distribution. Here is practice question number 3, which tests your understanding of data types and sampling methods. Let's first classify the variables. Student's ID number is a label, not a quantity that can be calculated, so it's categorical. Favorite school subject is a category, like math or history, so it's categorical. Number of hours spent studying is a count of hours, and hours are typically treated as continuous, so let's classify it as continuous. Now for Part B. The school has 100 students. We want a systematic sample of 40 students. To find our interval K, we divide the population size, 800, by the sample size, 40, which gives us 20. So, we will sample every 20th student. We need a random starting point between 1 and 20. Let's use 13. The sample would then include students 13, 33, 53, and so on, until we have 40 students. Finally, Part C asks why a convenience sample of the first 40 students is biased. This is a classic coverage error. The first students to arrive might be early risers, come by public transport, or be involved in morning clubs. They are unlikely to be representative of the entire student body in terms of study habits, favorite subjects, or socioeconomic background. Practice question 4 focuses on survey design and error. A council conducts an online survey. Its first question is, do you support the construction of a new recycling plant, which is vital for our community's environmental health? Part A asks for a problem with this question. This is a leading question. The phrase, vital for our community's environmental health, is a value judgment. It pressures the respondent to agree, regardless of their true opinion or other concerns. This biased wording would lead to measurement error, as the recorded support might not reflect genuine public sentiment. Part B asks why an online survey might suffer from non-response error. There are several reasons. People may simply ignore the email or social media post. They might not have the time or interest to complete it. Importantly, certain demographics, such as elderly people, might not be as familiar with technology, leading to their underrepresentation, a form of coverage error. Our final practice question is a comprehensive one involving a frequency table and a column graph. A rugby team's winning margins for 100 games are shown in this grouped frequency table. Part A asks whether winning margin is discrete or continuous. Rugby scores are always whole numbers like 1, 3, 5, etc., so a winning margin is a count of points, making it discrete data. Part B requires the appropriate graph. Since the data is discrete, we draw a column graph with gaps between the columns. The x-axis shows the class intervals for the margin, and the y-axis shows the frequency. Part C asks for the modal class. Looking at our frequency table or the column graph, the highest frequency is 35, which corresponds to the margin interval of 11 to 20 points. Finally, Part D asks for the distribution. The column graph clearly shows a single peak around the 11 to 20 and 21 to 30 intervals, with a long tail extending to the right, towards the higher margins. This is characteristic of a positively skewed distribution. Let's recap what we've learned in this session. We've established the foundation for any statistical inquiry. We began by defining the key terms: population, sample, census, variables, and the distinction between categorical and quantitative data. We then walked through the six-step process of a statistical investigation, from stating the problem to interpreting the statistics. We learned about the four main categories of error: sampling, coverage, non-response, and measurement, and saw how they can make a sample biased and conclusions unreliable. Crucially, we explored different sampling methods, emphasizing that simple random and stratified sampling are the best ways to ensure a sample is representative, while convenience and quota sampling introduce significant bias. We classified data into categorical, discrete, and continuous types and saw how this classification determines the appropriate visual displays: column graphs for discrete data and histograms with no gaps for continuous data. Finally, we covered essential guidelines for writing clear, specific, neutral, and ethical survey questions to avoid measurement error. Mastering these concepts is fundamental to success in the IB/AI/HL course. Keep practicing with questions like the ones we've done today, and remember that for personalized support, DAR Tutors is here to help you achieve your best. Thank you for watching.